programming languages. This class will focus more on the elegant mathematics than the practical engineering, but I'll try to make those connections all the way through and encourage students in the class to do the same. So we'll study these miniature languages. Sometimes when you study a little miniature language, a little model of a larger real-world thing, you end up proving really obvious things. Like if your program doesn't have any loops in it, then it terminates, especially if there's no functions or anything like that. And other times there's really non-obvious things that you can use these tools to prove. Like if they didn't put some hack in the language definition, C++ was actually defined in a way that the compiler wouldn't necessarily terminate, which is usually considered a bad thing. Okay? Another perspective that I think is great for looking at sort of programming languages is a language definition is just a function with a very rich input space. Because it has such a rich input space, being able to define what that function, the language, should be able to do really makes you better at sort of adversarial thinking and thinking about how your system works or should work, or any cases you haven't covered. So the way I like to think of it is my systems colleagues in the room. You know, when you build a complicated system like an operating system kernel or many other systems, they tend to be very wide. Thousands of entry points with pretty simple inputs and results. Simple to understand, simple to document each one of them, but the complicated part is how they all interact with each other. Programming languages goes deep and not wide. It says, look, all I've got is type check and compile. Right? 2 input points, simplest API in the world. The only catch is they take these things called programs. Right? And that the definition of program is so rich and elaborate that I kind of wish I had 3/4 instead of 1 to show you all the cool things you could do in understanding what a program is. I should also add that any extensible system out there eventually ends up defining its own programming language. Right? If you look at any extensible system, they all end up adding a scripting language. So even if you don't want to be a PL person, if you want to write an extensible system, you're going to end up with it. Okay, so a little more about the class. It is known as a very rigorous class. What we'll basically study is variables, control flow, scope, functions, objects, and threads. And you're like, I already know all those things. Yes, but you haven't studied them as carefully as we're going to. And it'll give you a very, very deep understanding of the building blocks on top of which we build all of our software and all of our computational abstractions. We do spend a lot of time on type systems. It's sometimes known as a course all about type systems. I've done the math, I looked at it. It's only about 40% about type systems. And even then, it's really as an organizing principle, as a way to understand the invariance and how you define data structures and functions and things like that. But yes, we'll definitely study type systems. On each of the homeworks, you're going to write things out with paper and pencil, puzzles, proofs, things like that. You'll also write some programs. The programs will all be in OCaml, not because of oompleFop, but because it's particularly well suited for the sort of things we want to investigate. And if you don't know it, that's totally fine. I don't expect you to. If you do know it, great. You can help out the people around you. At the beginning of the class, I'll spend a lecture and a half or so on a tutorial about it to get you up to speed, and that's all you need. There is a fair amount of theory aimed at the key questions. I think of it as a somewhat theoretical course. I think that's good for a lot of you. The homeworks are where you're going to learn the most, as good as I think I am in the lectures. Obviously, it's when you go and try to use this stuff and take it further, so we put a lot of thought into making the homeworks interesting. And at the end, you'll do a little writing assignment. We'll basically show that you've learned enough in the class that you can actually approach the research literature and read papers that, without having taken this class, would have been much less approachable. So that's kind of the payoff, and I want you to see that at the end of the class. So my goals for the class, right, are I want everyone who gets a PhD to take my class, right? And I want you all to, at the end of it, really know how to write down a precise definition, a precise computational model, and prove something about it. And if I can do that, I don't care if you don't learn anything about programming languages. But you will learn a lot about programming languages. In fact, you'll learn enough jargon that you can approach the literature. You'll also be able to write better programs, just because you'll understand how languages are put together. And you won't be like, oh, here's a random feature that just saved me 3 lines. You'll have more of the structure. You'll have more of the understanding. So my sales pitch is if you take this class, you'll be a better programmer because you understand the underpinnings under the language. You'll be a better researcher because you know how to make and prove rigorous statements. And just in case you're interested in programming languages research, you'll have a big chunk of the background you need to do that as well. I think this is my last slide, just some advice for if you do take the class or whatever. And my first piece of advice, don't ask me, I'm the professor, right? Like as students who've taken it before, a lot of the students in the department have taken the class and they probably have better advice than I do. But my take on it is that you don't skim the formal stuff. You don't think, oh, I don't quite get that definition, but I'll pick it up. Like, no, it all builds on it. You do have to get that. And I'll help you with that. But then what you have to do on top of that is not just look at this as, okay, well I got the definition, I solved the problem, but this has something to do with software I've written. And it's kind of up to me, and if I'm confused, ask Dan with what is that connection back to sort of what I knew before I took this class. And then the other thing I would mention is I think a lot of our quals classes tend to have more work toward the end, either because there's a project or because you build up to that or whatever. And I think mine is a little inverted that way, which can be a good match if you're interested in taking 2 classes. I know a lot of people give you the advice only to take 1. That I think it's more work at the beginning of the term. That it's kind of a new way of thinking about everything, and then maybe you've never programmed in OCaml, and the proofs are really detail-oriented. But then once you kind of get over that hump, then the payoff is we study lots of different things about programming languages, and in my view, the 5 homeworks are kind of all of equal length and difficulty, and then therefore in the student's view, they tend to kind of get easier kind of once you get the hang of it. And then I don't throw a bunch of extra stuff at you at the end, except that short writing assignment. Okay, so that's it, and I've got a minute or 2 for questions. Yes?
I saw that there's a PL course in Coursera.
Yes.
Online.
Yes.
Does that cover the same topic?
No. So the Coursera course by me, right, that's like my course for 2nd year undergraduates. So it's much more basic. That course assumes as a prereq just that you've taken like 1 or 2 programming classes before and you know what a linked list and recursion are.
Okay.
Yep.